the graphs of sine and cosine. Okay, the graphs of sine of x and cosine of x. So just notice that I'm putting the x inside of the parentheses because this is a function with an input. So you know how we do like f of x for our function notation? So x is going to be the input, so I just like to put the x in parentheses. Okay. All right, so let's start with sine of x, okay? So what does the graph for sine of x look like? Okay, so there's gonna be a lot of images today. Let's see, there'll be a lot of pictures in today's class. All right. Okay. So from our trig table, we actually have the values of sine at all of these nice angles, okay? So we have 0, pi over 6, pi over 4, pi over 3, and so on. So these are the inputs. And then the bottom row is just the outputs of the sine function. So this is just a good old-fashioned function table for sine of x. All right, that's all it is. It's just a function table. And from this, we can plot the points on the xy plane and see what the graph is going to look like. All right, so this is something that we've done before. We have our function table, and then we look at it in the xy plane. So here's the function table. This is nothing new. This is on the trig table. But now let's see the graph that it makes. Okay. Copy and paste. Okay, so this is what it's going to look like. It's kind of like this nice kind of curvy thing. So just note here, this is only the graph when the inputs are going from 0 to 2 pi. This will keep going on forever and ever in this shape. Okay, so we're just graphing like one cycle or one period of the sine graph. So I'm going to define what period means later, but it's going to look like this here, but it's also going to like continue this shape over to the left. Okay, so that's sine. All right, so now let's go over to, why don't we look at the graph for cosine now. Okay, and it's going to be pretty much the same story. So I'll show you guys the function table. So you don't need to copy this down because we have this from last class. So here's the function table for cosine. So the top row are our inputs or our x values, and then the bottom row are the outputs at these input values. Okay, so from this, we can now plot the coordinates on the xy plane to see what the graph is going to look like. All right, so let's just look at cosine. Okay, so it's like this. It looks very similar to sine. So look at sine, and then we have cosine. So it's actually, you'll see that it's the cosine graph is just the sine graph shifted to the, I think, right, pi over 2 units. Okay. So they actually do look the same. Their only difference is that one is a horizontal shift of the other. Okay. And again, this shape is going to continue infinitely to the left and right. So all I have graphed here is one period of cosine, and I'm going to define what period is, I think, right now. All right, so any questions about the graphs? So just function table and corresponding graph. These are what they look like in the XY plane. Okay, so the next thing we'll talk about is periodicity. Okay, so this was this period word that I was that I kept like alluding to earlier. So periodicity. This is a very nice definition. Okay, so definition. What does this mean? Okay, so definition. So a function is said to be periodic with period P if f of x plus P is equal to f of x for all x values. Okay, so the word I'm defining in this definition, or the words I'm defining, is the phrase periodic with period P. Okay, so it means that f evaluated at x plus P is actually the same as f evaluated at x for all x values. All right, so that's a really nice property. It's like, oh, I can shift my function to the left or right by P units, and I will land at the same Y value. Okay, so that's what this means here. So what's the connection to sine and cosine? Well, here it is. So the fact of the matter is that sine of x and cosine of x are periodic. They are periodic with period what? Sorry, my thing is not level right now. Okay, they are periodic with period 2 pi. Okay. So this is kind of like captured in, like, if you have an angle and you rotate it 2 pi degrees, you end up at the same exact angle. Okay, so sine and cosine cannot tell the difference between an angle and 2 pi plus that angle, okay, because they look the same in the xy plane. So that's kind of like the intuition behind it. So sine of x and cosine of x are periodic with period 2 pi. So what does this mean really? Well, it means this by definition. It means that sine of x plus 2 pi is equal to sine of x. Okay, that's a definition of having period 2 pi. And also cosine of x plus 2 pi is equal to cosine of x. Okay. All right, good. So I hope this is this kind of makes sense. This is a really nice definition.
When you say periodic, could you explain that part again? I mean, like, what exactly do you mean by periodic?
Yeah, so periodic, it just means it satisfies this functional equation. F of x plus P, where P is some fixed number, so P is going to be specified. It's going to be the same as just evaluating F at x itself. So for the case of sine and cosine, the P is 2 pi. So you see how I'm evaluating sine and cosine at x plus 2 pi, but I'm getting the same output as if I was just evaluating at x itself. So that's what periodic means. It means I can shift my function horizontally to the left or right by P units, and I end up at the same Y value. Okay, so graphically, what does this mean? So graphically, this means the graph of sine and cosine will repeat every 2 pi units. Okay, so that means, like, if I travel 2 pi units to the left or right on the x-axis, the graph is going to look exactly the same. All right, so this is going to be much clearer when I show a picture of it. So let's go to that. This is a really nice picture.
Will 2 pi be your input?
No. That's not the input. It's just, hold on. So it means that I travel, so I start here at 0. I don't need to, but I start here. I start anywhere on the x-axis. Let me start at 0. If I travel 2 pi units, the graph is now going to repeat itself again. It's going to be the same as it was over here. Start at 2 pi, it's going to have the same exact thing. Again, the same exact thing. So it just goes on in this same pattern, okay? So this happens every 2 pi units. Okay, so this is for sine of x, but the same is true for cosine of x. So you travel 2 pi units to the right. Oh, look, I ended up at the same spot. Okay, I'm at 1. And then the graph will just keep repeating itself every 2 pi units. So this is the graphical interpretation of what it means for a function to have period 2 pi. Okay, every 2 pi units, I will land at the same y value. So look, I don't need to start at 0. Let me start at pi. At pi, I'm at the y value 0. Travel 2 pi units. 1 pi, 2 pi. Look, I traveled 2 pi units and I'm back at 0. Okay? So that's what it means. It means if I travel 2 pi units to the left or right, I will land at that same exact y value that I was at before. All right, and you can test this on any point you want. Okay, so any questions about this? Okay, good. All right, so now we're just going to talk about like the domain and range. Maybe you can even see what the domain and range is just from looking at the graphs. So maybe think about that as I'm about to write it. So I'm going to just talk about the domain and range of sine and cosine. So maybe just think about that and see if you can guess. Okay, so they actually both have the same domain and same range. So would someone maybe like to give it a guess? So domain is what? And range is what? So can we look at these graphs of sine and cosine and determine domain and range?
I'm going to guess that domain is negative infinity to positive infinity, and range is -1 to +1.
Excellent. That is 100% correct. Yeah. So it is. So the domain is negative infinity to infinity because these arrows indicate that the graphs go on forever. Okay. So all x values are permissible to put into this function. So very good. Domain, our allowed x values, is the whole real line. So it's minus infinity to infinity. But how about the y values? What y values do we hit? What's the range? Well, the only y, so we're never going above 1. And we're never going below 1. But we do hit those 2 values, so we're going to need closed brackets. Okay, so the closed interval, -1 to 1. All right, and the reason why they're closed, the reason why we have the square brackets is because we're actually hitting 1 and -1. They are included in our set. Okay, so very good, very good. So that's domain and range. Excellent. Okay, and also we also have some nice other properties. So sine of x is actually an odd function. Is an odd function, and what does that mean? Well, it means that sine. Oh no, I shouldn't use a hyphen there. That's not good. So what it means is that sine of -x is the same as negative sine of x. Okay, so that was the defining property of what it means to be odd. It means I can pull out a minus sign from the input and it comes out as a minus sign on the whole function. So that's for sine. It's an odd function. It's symmetric about the origin. And how about cosine? Well, cosine is even nicer. Cosine is an even. So it's so beautiful. It's an even function. And what does this mean now? So let's think back to our days when we did even and odd functions. Well, this just means that cosine of -x is the same as evaluating at cosine of x itself. And the graphical interpretation of this, it's that it's symmetric about the y-axis. So you can actually look at this and see that for yourself. So look at cosine. This is exactly itself. It's an exact reflection of itself across the y-axis. So you can kind of fold it on itself and it lands perfectly. And sine of x is symmetric about the origin. Okay. So really nice, really nice properties. So any questions? Okay, so those are the basics. Those are the basics. Now, of course, we need to talk about transformations. All right, so we have a function, but of course, we can do all of our lovely transformations to it. So let's now deal with that. So transformations of sine and cosine. Okay, very good. So in general, a transformation of sine and cosine look like, okay, so in general, a transformation of sine and cosine look like, or looks like, I think this should be looks like, let me see, a transformation looks like, yeah, because transformation is singular, yeah. So a transformation of sine and cosine looks like, so this should look somewhat familiar. So we have y is equal to capital A times sine of b multiplied by x plus c plus d. Okay, so that's for sine, and of course we also have the same thing for cosine. So capital A times cosine of b times x plus c, and then plus d. Okay, so I hope this looks familiar. This is like how we always transform functions. We have our vertical stretch here. We have our horizontal stretch or compression B. Our C is our horizontal shift, and D is our vertical shift. All right, so nothing new here really, but we do have some different terminology, unfortunately, for these A, B, C's, and D numbers. All right, so I'm going to get to that in a second. First, let me just show you some pictures. Okay, so we're going to get to these letters A, B, C, and D in a second. So, but first, let me just start off with some like motivating examples. Let's just see what's going on here. Okay. All right, so what do I have here? Okay, very nice. So this is a very nice picture. Let's see. Okay, all right, sweet. So this, okay, so it looks a little crazy, but it's not. So all I have here, I have four functions graphed. I have sine of x, 2 sine of x, 3 sine of x, and 4 sine of x. And the effect of changing this number, 1, 2, 3, and 4, is that the graph is going to stretch, okay? Because remember, when you multiply the outside of a function by a number, that's a vertical stretch, all right? So all we're doing here is just vertically stretching the sine function, all right? So I also want to show you guys another connection. When the coefficient is 4, look at the highest value that the graph gets to, it is 4. When the graph is 3, the highest value the graph gets to is 3, and so on. Okay, so this coefficient kind of tells you the highest point that you're going to hit, right? All right, so that's nice. So let me just kind of write what I just said. So we see here, that when the vertical stretch increases, the graph gets taller. Okay, very good. All right, so what do I, okay, good, yeah, nice. All right, so really nothing new here. It's just our old stuff applied to the specific function sine of x. All right, so we have this vertical stretch going on. But what's cool is that the coefficient will tell us the highest point that the graph hits. So 4 sine of x has a maximum value of 4, and 3 sine of x has a max value of 3, and so on. So that's a nice property. All right, let's go to another example. Let's do y is equal to sine of x plus 2. Okay. Okay, first of all, would anyone like to tell me what transformation this will be of the sine function? What are we doing to it? What type of transformation is this of the sine function?
That would be a vertical shift.
Yes, exactly. So more specifically, a vertical shift of what?
2 units. Yeah,
What?
vertical shift of 2 units.
Yes, yes, thank you. Awesome. Exactly. So, so we have this plus 2 on the outside of the function, and from our previous work, this is definitely a vertical shift up 2 units. So very good. So let's just write that. This is a vertical shift up 2 units of the sine function. Very good. So we're taking the sine of x function and we're just shifting it up 2 units. So let's see what that looks like. Very good. So it's exactly what you would expect it to be. It's quite nice. Here we go. So in blue, we have like the parent function or the toolkit function where it's unchanged. It's just itself. And then up in the orange, we have a vertical shift up 2 units. All right. So look, this value 0, that went up to 2, and so on. Okay. So we did go up 2 units. Very good. Very good. All right, good. So now I need to tell you the special names that we give A, B, C, and D in the case of trig functions. So yes, they still are vertical stretches and horizontal stretches and vertical shifts and horizontal shifts. But for some reason, in the special case of trigonometric functions, we give these letters different names. Okay, so let me just go through that now. Okay, so I'm actually just going to copy this down again because we're going to use it. Okay, so I'm going to copy this down again. Good. Okay, so let's see what's going on here. All right, so this is really just like a definition. Okay, so the absolute value of A, which is, looks like that, is called the amplitude. Okay, that's called the amplitude. All right, so it's just the absolute value of the vertical stretch. Okay, that's called the amplitude. Okay, what else do we have?
Could a vertical stretch also be negative or no, it cannot?
Oh yes, of course, yeah. So that would be a vertical stretch combined with a reflection
Okay.
about the x-axis. Yes, all of the reflections are still hold, absolutely. Okay, good. So that's that. C is called the phase shift. So that's kind of fancy sounding. C is called the phase shift. Okay, so it's not called a horizontal shift in this context. It still is a horizontal shift. Don't get me wrong here. It is a horizontal shift, but we just give it this special name of phase shift. So B doesn't have a special name, so don't worry about B. And then last, the line y equals D is called the midline. Is called the midline. Okay. So that's really, so that's kind of the terminology that's attached to the transformations of sine and cosine, all right? Okay, so I have two kind of important facts. So two important facts here. Okay, so fact one is going to be, maybe I'll type this, make it easier. So the distance from the midline to the highest part of the graph will be the amplitude. Okay, so you go to the midline and then you travel up to the highest part of the graph that is attained. That will be the amplitude. Okay, and second, I'll have to write this one. The period will be, this is a very important equation. So you can get the period of your graph just by looking at the formula. It's going to be 2 pi divided by capital B, that horizontal compression. All right, so to get the period from the formula to the algebraic formula, you're going to have to do 2 pi divided by B. 2 pi divided by the horizontal compression. Okay, so these are really nice facts, and we're going to use them from time today. All right, so here we go. So let's now look at a nice example. So let's look at y is equal to 3 times sine of 2x plus 1. So what I want, so really what I want you guys to tell me is the amplitude, the midline, and the period. Okay, so I'm giving you an algebraic formula for a function. Like, tell me like its properties. Tell me the amplitude, midline, and period, and phase shift if there is one. Okay, very good. So let's just kind of go through it. So I'm going to go in order from A, B, C, and D. So here, the absolute value of A is the absolute value of 3. All right, so A is this coefficient, which is 3. Okay, so the amplitude is 3. Good. Okay, next. What is our B value? Next, B is equal to what? Well, you just have to go to the coefficient of the input x. It's 2. Okay, now I want to find the period from this. So we know that P, which is the period, will be 2 pi divided by the B value, 2 pi divided by 2. Okay, so that one right here. Okay, so thus, the period P is what? Well, I'll just do 2 pi divided by 2. That's just going to be pi. So the period's pi. Excellent. Okay, good. And finally, now let's just do D. Capital D is 1 because there's a plus 1 at the end. So that tells us that the midline is y equals 1. Okay. D equals 1. So the midline is y equals 1. All right, so that's really all you have to do here. And just note there's no horizontal shift, there's no phase shift, okay? All right, good. So I do have a picture of this graph so we can kind of see what we're looking at. Oh, okay. I forgot to show you guys this. Okay, I'll show that after. All right, anyways. Right, so here is the picture of what we just did. Good, so the midline is y equals 1. You can see that right here. Excellent. The distance from the midline to the highest point on the graph is 3, because the highest point on the graph is 4, and the distance from 1 to 4 is 3. So that's the amplitude. And you can see that the graph completes one cycle in pi units. So the period's pi. So that's another way to interpret period, is how long does it take for the graph to complete one cycle? I forgot to say that earlier. So you can see visually that it has taken pi units to complete one cycle. Okay, so the period's pi. All right, so that's all of this information that we discovered, but in the graph. All right, so any questions? Okay, good. So here's this picture from before that I forgot to show you guys. So let me just, I think it's kind of redundant at this point, but let me just get it on here. So the picture, it's just kind of showing all of our terminology, but on a graph. So we have the amplitude is the distance from the midline to the highest point. The period is how long it takes to complete one cycle. And we have the midline. Okay. All right. So any questions? All right, so let's do another example. Okay, so how about f of x is equal to sine of x plus pi over 6. Just give me 1 second, hold on. Okay, sorry about that. Yeah, so all this one is sine of x plus pi over 6. The only thing that's going on here is that we have a horizontal shift of pi over 6 units. Okay, so that's from there. So this has a, so now we call it a phase shift of pi over 6 units. Now, is it to the left or to the right? Well, if we're talking about horizontal shifts, a plus means we're going to the left. So it's pi over 6 units to the left. Okay. Right. So really what I'm trying to illustrate here is this new terminology of phase shift. Okay. Okay, let's do another maybe more interesting example. Okay, so find the amplitude, period, phase shift, and midline of y is equal to 1/2 cosine of 1/3 times x minus pi. Okay, so I'm giving you an algebraic formula for the transformation of cosine, and I want you to tell me the amplitude, period, phase shift, and midline of it. Okay. Okay, so let me just identify what A, B, C, and D is here. So here, so A was our vertical stretch, so that's gonna be 1/2. B is 1/3. C, our phase shift, is minus pi. And D, What's our vertical shift? There is none, okay? There's nothing being added or subtracted outside of the function. So it's actually just 0. D is 0. Okay. So now let's kind of roll through it. So the amplitude, remember, it's the absolute value of A, which is going to be the absolute value of 1/2, which is 1/2. That's the first thing. Okay, here's maybe the more tricky one is finding the period. So the period, remember, it's 2 pi over b. That's how you find the period. It's 2 pi over b. So it's going to be 2 pi over 1/3. Okay, so you need to figure out, you need to do this computation here, this arithmetic. So you do 2 pi divided by 1/3. Well, that's just like dividing fractions. That's going to be 6 pi. Okay, so that's the period. Very good. Next, the phase shift is, okay, so it's minus pi, which means we're moving pi units to the right. So the phase shift is right pi units. Very good. And the midline is y equals 0. Okay. So let's just take a second to absorb this and see if you have any confusions or questions. Okay, so if there are no questions, I will move on. All right, so what did I want to do? Okay, so I want to return to the previous example of 3 times sine of 2x plus 1. So this is kind of like a new thing we're doing now. So let us return to the previous example. Of y equals 3 times sine of 2x plus 1. All right, so let me just grab that image. I think I have it here. Yeah, it is right here. That's good. Okay, so what I really just wanted to make note here is that the midline is precisely halfway between the lowest and highest points of the graph, okay? So like, look, the lowest point of the graph is y equals -2. You see that? And the highest point is y equals 4. So you call these the minimum and maximum values if you want to be technical, like that's the correct terminology in like math, in math terms. So the minimum value is -2. The maximum value for this graph is 4. And you'll just notice that the midline sits exactly in between, in the midway between the minimum and maximum. Okay. So I'm going to just type this quickly because it is pretty important. So we see that the midline is halfway between the lowest and highest points. So that's the minimum and maximum on the graph. So namely, y equals -2 and y equals 4. Okay, so again, the midline sits exactly halfway between y equals -2 and y equals 4. The midline will sit right exactly in the middle of those 2 points. Okay, and why do we care about this? Okay, well, this will help us in identifying graphs. Okay, so that's going to help us when we are given a graph to find its formula.
And this is just for one period.
This is going to work, no, it will work anywhere on the graph, not just for one period shown.
No, I mean like the spectrum.
What was that?
That's okay. I got it.
Okay. Okay, so we're gonna now go to an example, okay? Okay, so example, let's try to find the equation of the following graph. Okay. Okay, so this is kind of like the next part of class is like I'm going to give you a graph and I would like for you to tell me the algebraic formula that this graph represents. Okay, so first of all, this is going to be a shift of the sine function. So let's get that down. So we see that this is a shift of the sine function. Okay, so remember what we need. Like we need to find like A, B, C, and D, and we're going to be done. Okay, so what do we need to find? So we need to find all of those special letters, A, B, C, and D. Okay, so let's actually start with D, which is the midline. So the midline, as I just said above, is going to sit exactly halfway between the minimum and maximum values. So that's the nice thing about this. So let's talk about that. So the minimum, oh, okay, hold on. Okay, so the minimum, sorry, hold on. Right, so the minimum value for this graph, so we just need to look at the smallest y value that this graph is hitting, and that's 1. So the minimum value is y equals 1, and the maximum value is what? Y equals, so go to the graph. What's the biggest y value that we're hitting here? It's actually 3, is y equals 3. So the midline is going to sit exactly in between, halfway between the minimum and maximum value, okay? So what's that going to be? Well, if we're the halfway between 1 and 3 is 2. So that's going to be the midline. That's going to be D. So here's the midline right here. Okay, so D equals 2. And the midline is y equals 2. Okay, so we just figured out our first piece of information for finding the equation of this. D equals 2. Excellent. Okay, now the amplitude. The amplitude will be the distance from the midline to the maximum value, y equals 3. Okay, so what's the distance from the midline, which is 2, to the maximum value 3? So what is this distance here? Well, that's just 1. Okay, so that's what the amplitude is. It's another way to think, another way to define it. It's the distance from the midline to the maximum value. Okay, so the amplitude, which is absolute value of A, is 1. Okay, so far so good. Okay, now to find B, we need to find the period. Okay, so recall that the period will equal 2 pi over B. So we need to find the period, and then we solve this equation for B. So we need to look at the graph and be like, oh, how many units will this graph until it repeats itself? Okay, so that's what the period is. How many units does it take for this graph to complete one cycle? Well, one way to do that pretty quickly is to kind of just measure the distance from the 2 maximum points here. That's a nice quick way to find the period. So what's the distance from this maximum point to this maximum point? Well, it's hard to tell. Maybe that's not the best way to do it. In this case, it's probably best to just look at it and see how long it takes to complete one cycle. So here's one cycle, and that was 2 pi units. Okay. So I hope everyone agrees. It took 2 pi units to complete one cycle of this graph. Okay. All right. So I know this is kind of long, but let's just kind of stick with it. So from the graph, we see that the period is 2 pi. Okay, you can see that the graph completes one cycle in 2 pi units. So we solve 2 pi is equal to 2 pi over B to find B. Okay, so I just substituted in 2 pi in for the period in this equation, and that's how we find B. All right. So it should be pretty easy to solve this. This gives what? B is equal to 1. Capital B is equal to 1. Okay. So I think we're finished now. So thus A equals 1, B equals 1, and D is equal to 2. Okay, so our final formula is y is equal to sine of x plus 2. That was it. Okay, so A is 1, B is 1, and the plus 2 for D at the end. Okay, so here's the final answer. All right, so I hope everyone's okay. I'm not really hearing from anyone, so.
Where would we see a phase shift on a graph?
Oh yeah, so first of all, this one has no phase shift. But the phase shifts for the trigonometric functions are actually kind of tricky. There's really no like set way to see it. So I'm actually in this lecture and on our homework and exams, we're not going to consider phase shifts really, because they are kind of tricky. So I would just say do not worry about them right now.
All right, cool, thank you.
Yeah, you're welcome. All right. So we're going to do like, I think 2 more of these just to kind of, just to kind of get some practice with it. Okay, so next one.
I do have one quick question, I'm sorry.
Yeah.
How did we differentiate between a sine and a cosine graph up there?
Yeah, so that's another tough thing because the cosine and sine graphs look very similar. In fact, they're just a horizontal shift of one another. But you look that the sine graph, it starts like that, but the cosine graph starts like that. So that's the way I like to think of it. So this one has this kind of behavior at the y-axis. It starts up and then it goes down. Whereas at the y-axis, cosine goes down, then up.
So an upward versus a downward trend.
Yes, starting at the y-axis. Yeah, start at the y-axis. Is it going up or is it going down? But this is only in the case when there's no horizontal shift, but we're not doing horizontal shifts, so this will work for us. Yeah, good question. Thank you. Yeah, so, but I'm actually going to tell you what function to work with. So, yeah, so actually just look at how I word this question. I'm actually going to tell you which one to do. So usually the question will be posed as this. Find an equation involving the sine function. So you're not even going to have to guess. Find an equation involving the sine function from the graph shown below. Okay, so let's get that graph. Where are we? Right, awesome. Okay, so I'm telling you that it's going to be some transformation of the sine function, okay? So there's no guesswork there. Okay, so what we need to find A, B, C, and D. We need to find the amplitude, the midline, phase, well, there's no phase shift here, and the vertical shift, okay? All of that. Okay, good. So I'm just going to start. I always like to start with the midline because it's literally the midway point between the minimum and maximum. So I like to start with that. So max here, what's the maximum y value of this graph? What's the biggest y value that this graph actually hits? Well, you can just look. It's just going to be -1. So max is -1. And what's min? What's our minimum? What's the smallest y value that this graph hits? That's going to be -5. And I start with this because halfway between the maximum and minimum will be the midline. Okay? So the midline will be at, okay, what's halfway between -5 and -1? Well, that's just going to be -3. Okay, that's precisely halfway between -5 and -1. So here is that midline. I'm just going to do a dotted line at it. Okay. We'll be at y equals -3. So capital D is exactly -3. Okay. Very good. Now, to find the amplitude, you just do the distance from the midline to the maximum. Okay. So next, the distance from -3 to the max, -1, is, well, you just need to look at how many units the midline is from the maximum. And that's 2 units, because from -3 to -1, that's a distance of 2. Okay, so that's going to be 2. So the amplitude, A is equal to 2. All right, so we're almost done here. So we have D and we have A. Okay, what else do we need here? Right, okay, so the most interesting part is finding the period. So we see here that the graph repeats itself, and I'm going to scroll up, repeats itself every blank units. And this blank is going to be the period. All right, so let's scroll up and look at what the period is. Okay, how many units does it take for this graph to complete one cycle? Well, you can just kind of start here. So we go, we go, we go, we go. So from 0 to 4, it took us to get a complete cycle. Okay, so thus it took us 4 units. That's the period. So I hope everyone sees that. I start here and I see how long it takes me to finish one complete cycle. And where we ended up was at 4. Okay. So that's the period. Well, let me scroll back down. So we see here that the graph repeats itself every 4 units. So the period is 4. Okay. So now we need to find B. To find B, you solve. You set the period equal to 2 pi over B. Okay, this is how you find the period. This is how you find B. You need to set the period equal to 2 pi over B. So this is very easy to solve. You can just like cross multiply or multiply both sides by B, and you'll just get that B is equal to pi over 2. Okay, so B is pi over 2. And I think that's it. I think we have all of our data. We have all of our letters. Yeah, so D is -3, A is 2, and B is pi over 2. So we are done. So the answer will be y is equal to A, so 2 times sine of bx, so pi over 2 times x, plus the midline, which is -3, -3. All right, so that's the algebraic formula for the graph for this graph.
I hate to ask, but can you do the arithmetic for 4 equals 2 pi over b?
Absolutely, yes, definitely. So let's just kind of isolate on this right now. Okay, but do you see why I'm solving this equation though, firstly? Okay, good. All right, so let's just solve this guy. Right, where did it go? Okay, whatever, I don't know, it's not working. Okay, so 4 is equal to 2 pi over b. So we're solving for b, so you can actually think of this as a rational equation because the variable we want to solve for is like in the bottom of a fraction. So the LCD here is b, so you multiply both sides by b. So I'm going to multiply by b here, and I'm also going to multiply by b on the right side. So I will get 4b is equal to 2 pi, which means that b is equal to 2 pi over 4, which is pi over 2. So it's the same set of steps for solving a rational equation. Good, so that is that. Awesome. Okay, I do have one more. I'm just thinking if we should do it or not.
Could you show where you got the -3 from? One more time.
Yes, that is halfway between the minimum and the maximum.
Oh, okay, so the vertical shift is just the midline, basically.
Yes, exactly. It's whatever your midline is. Yes, exactly. That's the connection. Yeah. Good. All right. I don't know if I should. I have one more example here. I don't know if I should do it or if we should go to the review. I don't know. Does anyone have an opinion? Should we do one more of these or should we go to the review?
Can you do one more?
Yeah, definitely. I will move a little faster just in the interest of time, but yes, definitely. Okay, we're going to do one more. So find an equation. Find an equation involving the cosine function. So I'm going to tell you which function you're going to want to transform. Okay, there's little to no guesswork here. Find an equation involving the cosine function. For the graph shown below. Now just remember, this stuff will not be on the exam Thursday, by the way, okay? This is not on the exam. Find an equation involving the cosine function for the graph shown below. Okay, good. So let's get that graph. Awesome. I think this is, I hope this is it. Yeah, this should be it. Okay, excellent. Good. So we have some graph here. I'm telling you it's some transformation of cosine. So I'm going to follow the same format I did before. I'm going to find the minimum and the maximum. Then from there, I find the midline. Then from the midline, I find the amplitude. And then I end with the period. I think that's a nice logical set of steps. So minimum, yeah, I'll start with maximum just to keep it consistent. Okay, so maybe someone can kind of help me out to finding the data here. So what's the maximum y value for this graph and what's the minimum? So maybe someone can look and tell me.
3 and -1.
Yes, excellent. The highest y value that we hit is 3. Very good. And the minimum or the smallest y value we hit is -1. Good. And why do I care about this? It's because the midway point between these 2 points will be the midline. That's why I start with this. Okay, good. So the midline will be exactly halfway between the minimum and max. Okay. So what's halfway between -1 and 3? That's actually 1. Okay, y equals 1. So it's something like right here. Okay, so the midline is y equals 1 because that's halfway between -1 and 3. Okay, but the midline tells us what D is, what the vertical shift is, okay? Thus, capital D, the vertical shift is 1. So we have our first piece of data done. Excellent. Now, the amplitude will be the distance from the midline to the maximum. Or, I didn't say this before, it's also the distance from the midline to the minimum. Same thing. It will give you the same thing. Okay. So the distance from the midline, 1, to the maximum, 3, is, well, what's the distance from 1 to 3? That's 2. 3 is 2 units away from 1, or 1 is 2 units away from 3. Okay, so the amplitude is 2. That's what we just found out. So the amplitude, which is A, so the amplitude A is precisely 2. Good. Okay, the next step we need to find B, which is the horizontal compression. And in order to do that, you need to find the period. Okay, so how many units does it take for this graph to repeat itself? Okay, how long do we need to travel on the x-axis? How far do we need to travel on the x-axis for this graph to repeat itself? So let's think about that for a second. So I'm just going to start writing. So the graph repeats itself every blank units, and that's the period. So we're finding the period right now. The graph repeats itself every blank units. Okay, so let's scroll back up and look. So, any ideas?
I would say every 2 units.
Very
Nothing.
good. So what did you see here that made you think that?
I saw at -1 and 1, the graph begins the same behavior.
Well said. Perfect. So in this case, it was really nice to see that these minimum points, they landed right on -1 and 1, which allowed us to measure the distance nicely. Good. Excellent. So the graph repeats itself every 2 units. Good. So that's the period. So So the period is 2. And to find b, remember that equation we need to solve. To find b, we solve period equals 2 pi over b. So we solve, the period is 2, so I'm putting that on the left side. 2 pi over b. Thus, b equals. Okay, so this is another technically a rational equation in the variable b. You can just quickly see here that b is going to be pi. That will satisfy this equation. And that is it. We are done with the question. We just need to like put all of our data together. So d is 1, a is 2, and b is pi. So here's the answer. Here's the answer. Good, so it's y is equal to a, so 2. Now we're doing cosine here, so I'm putting a cosine. B is pi, so pi times x, and then you do the midline, which is 1. So it'll be 2 times cosine of pi x plus 1. Okay, so hopefully not too bad. I think once you get the hang of it, these questions are actually kind of fun. I think they're kind of interesting. So we're going to have some of these questions on the next homework, like homework 10. But don't worry about it now. This will not be on the exam Thursday. Okay. All right, good. So if there are no questions, I will do a very quick exam 3 review.
I had 2 questions actually.
Sure.
For the unit circle, what coordinates fit on the unit circle? Like, does it, like after 1 comma 0, does the numbers 2, 3, the rest of them go after that, or no, only in between?
Oh, so the unit circle, so here's the unit circle. It's going to pass through these coordinates, 1, 0, 0, 1, negative 1, 0, and 0, minus 1. It's not going to hit 2, 3, which you just said. No. Okay. It will not pass through that point. So here are the points. So the only thing that we don't really have a hold of are these like intermediate points. There's, I don't, you can't really like pinpoint them exactly, but we know for sure it has these 4 though.
So it only hits those four main points and everything in between.
Yeah, yes, and it is everything in between. Yes.
Okay.
Absolutely. Yeah.
There was also another one though. You remember that question I asked you concerning that why the hypotenuse is going to be 1 because of the same radius as distance as 1. I looked at some website. I thought of it this way. I wasn't sure if this was a correct one. They said that if you were to increase the number, so for instance, they gave this the equation x squared plus y squared equals 1, that even if you were to increase it, like for example 2, like if you were to double it, then in that case you would also have to double the other variables too. Is that like one way to look at it? I mean,
double what exactly? So yes, we have the equation x squared plus y squared equals 1, which is the equation for the unit circle.
So for instance, if you were to switch 1 with the 2 or any other number greater than 1, it would be the same as doubling it, the other variables. So, I mean, I don't know if that's the way to look at it though. Like for instance, if you were to double 1 to 2 to make it 2, you would also have to double the other variables too. Like make it 2x squared plus y squared plus 2y squared.
Well, the thing with that, so if you double, so you take the coordinate 1, 0. If you double 1 and make it 2, that point, no matter what the y coordinate is, 2 comma whatever, that's not going to be on the unit circle anymore. That will not satisfy this equation ever. So maybe I'm misinterpreting your question.
Perhaps, but I think basically my question was that like why does it have to be 1? Like for example, like how, I mean, when I get that the radius has to be 1 and according to the unit circle, but if the radius was another number, like if it was 2, for instance.
Oh.
Yeah.
Yeah. Okay.
Then
It was 2. Okay. If the radius was 2, the set of points that satisfy it would be instead x squared plus y squared equals the square root of 2. This is a circle of radius not 1, but of 2.
would you still get the same answer though? I mean,
No, this is going to be a smaller circle. No.
Hmm.
Yeah, no. So this is not, you're not, so like your trig stuff, like the sine and cosine stuff, I don't think is going to work on this circle. But
so
it,
the radius, I see. So the radius is made to be 1, so that way you can see like a direct relationship between the trig functions.
yes, it works out very nicely when the radius is exactly 1. But I think you can still get some of the trig values maybe on a different radius circle.
I see.
I need to think about that, but we like the unit circle though. It makes things a lot easier. But you can probably do the same kind of stuff on like a circle of radius 2.
Got it.
Yeah, I'll have to get back to you on that. But yes, that's a nice question. Yeah.
I found a website on that. I'll send that to you to see maybe
Okay.
if you might get it.
Yeah, please. Yeah. Send that to me, like email or text me that. That'll be good. Thank you. Okay, good. All right, so let's just do a short exam 3 review. I'm pretty much just gonna hit like most of the topics that will be on the exam, and of course you guys can ask me questions that you have. So let me go through my stuff first, and then if you guys have any stuff, you can ask me. Okay, so we're just gonna move into exam 3 review. Okay, so the first thing will be an inverse function table. So I'm going to give you a function table, something we're like very familiar with now. So let's just say 1, I'm just making this up on the spot. So 1, 2, what else? 2, 2, and how about 3, 7? Okay, so I want you to tell me what's going to be the function table for the inverse. Okay. Oops. For the inverse, and remember we notate that with an f to the minus 1. Okay, that's the symbol for the inverse function to f. So give me a function table for the inverse. So what you do here is you literally just swap the 2 rows. So this bottom row of 2, 2, 7, that just becomes the top row. That becomes our inputs. So it'll become 2, 2, 7, and the top row now becomes the bottom row. So I have 1, 2, 3. Okay, so the question I'm going to ask you is to do this, and you need to tell me, is the inverse table a function? Okay, that's going to be the next thing I'm going to ask you. So is the inverse table, does the function table for the inverse satisfy the definition of a function? Okay. Okay, so this is a very easy question. So I don't know if you guys just aren't at your computers or I don't know what's going on.
It's not a function.
It's not a function. Good, thank you. And just, would you like to tell me why quickly?
Yeah, there are 2 and 2 are twice. There's 2 inputs have different outputs. I mean,
Yeah.
2 same input have different outputs. Sorry.
Exactly, yes, exactly. So 2 goes to 1, but 2 also goes to 2. That's no good. We need each input to have a unique output. So the answer is no. 2 has 2 distinct outputs. Very good. Okay, so that will be something I'll ask you next. So I'll just kind of number this. That was number 1. Number 2 will be to find the inverse. Find the inverse of y equals 3x plus 2. Okay, so I'm giving you a function and I would like for you to produce the inverse function. Okay, so let me just go through how you do this. So firstly, you want to swap the x and y variables. So you now make this x is equal to 3y plus 2. And now you solve for y. You literally just have to isolate this equation now for y. So this would be x, yeah, okay. So this would be 3y is equal to x minus 2. Divide both sides by 3. You'll get y is equal to x minus 2 over 3. Done. So expect something of this level on the exam, all right? So I hope that's clear. Good. So number 3, there's going to be a compound interest formula question. Okay, so I'm not going to go through an example because it's really just as easy as plugging in to the formula. Okay, but here's the formula though, just so you can get just be familiar with it. It's the account value is equal to the initial, the principal, plus 1 over r over n to the nth power. So r is the interest rate in decimal form. Okay, so that's really maybe the thing to remember. You need to convert that interest rate into decimal before you can plug it into the formula. All right, and I will tell you right now, you're going to be solving for the left side of the equation. Okay, so remember on the homework, I had you guys solve for P. That's not going to be, it's going to be even easier. I'm going to give you all the data for the right side, and you just give me the account value after a certain amount of years. Okay, so that's what's going to happen on the exam. You're going to solve for the left side. Okay, how about converting between logs and exponential? So log base b of x is equal to y is equivalent to, all right, so hopefully we're pretty fluent in converting from logarithmic to exponential. This is equivalent to b to the yth power is equal to x. Okay. So that's pretty much that. You're going to have some questions like this. Okay. All right, next. How about transformations of the logarithmic function? So f of x is equal to a times log base b of x plus c plus d. This passes through the points. This will pass through the points. So this is kind of nice. It passes through the points 1 minus c comma d and b minus c comma a plus d. Okay. So this a, c, and d value, those are our transformations, and b is the base of the logarithm. Okay. All right. So that's nice and easy. Okay. How about the domain? Domain of log base b of x. Okay, what are the set of allowed x values to plug into a logarithm? What is legal? What's permissible to substitute into a log function? Well, that will just be 0 to infinity, all right? Not including 0. It's the open interval 0 to infinity. All right, so here's a quick example. Find domain of natural log of 2x minus 6. Okay, so the domain, remember, you can only substitute x values that make the input to be greater than 0. So how do we find those x values? You just set the input to be greater than 0. So you set the input 2x minus 6 to be greater than 0. And solve. Okay, so let's just do that very quickly. Okay, so 2x minus 6 is greater than 0. This is a simple inequality. I think you guys can handle this. This would be 2x is greater than 6. Divide both sides by 2. This is x is greater than 3. Now put this into interval notation. it's going to be open, it's going to be the open interval 3 to infinity. Okay. So any questions so far? Okay, good. How about exponential equations? Okay, so how about you solve 3 to the 2x is equal to 9 to the 5th. So what you want to do is you want to create by creating like bases on both sides. And what you do is you really just need to think like, oh, 9, well, 9 and 3 have a nice connection to each other. 9 is equal to 3 squared. Okay, so what you do is you rewrite 9 as 3 squared. Okay, so what does this look like? You get 3 to the 2x is equal to, I replace now 9, so 9 to the 5th, I replace 9 with exactly 3 squared. Now I use properties of exponents. 3 to the 2x is equal to 3 to the 10th. Okay, so do you guys see how I can multiply these two exponents together and it becomes 3 to the 10th. Now use, this is like the one-to-one property, and equate the exponents. Okay, so you solve. So the exponents here are 2x and 10. You solve 2x is equal to 10, and this will give you a solution of x equals 5. There we go. All right, so any questions on this? I know I'm moving like super fast right now, but hopefully you guys are kind of strong on this topic because we had our homework assignments. Okay. All right, good. So last thing I have prepared is, so what number? All right, so we're on 8. I'm going to give you guys a logarithmic equation, and I want you to use the one-to-one property. So use one-to-one property to solve. Okay, to solve log of x plus log of x minus 2 is equal to log of 3. Is equal to log of 3. Okay, so remember the remember the one-to-one property. If log of x equals log of y, then x equals y. In order for us to use the one-to-one property, I need a single logarithm on both sides of the equation. I don't have that currently because I have 2 logarithms on the left side. So what do I can use the product rule of logarithms to make one logarithm on the left side. All right, so you just multiply the 2 inputs. So this is the same as log of x squared minus 2x is equal to log of 3. All right, so everyone good from here to here? This is the product rule. And I'm doing this as a preliminary step so I can apply the one-to-one property. All right, I need a single logarithm on each side. Good. Now use 1-1 property. I can set those inputs equal to each other. X squared minus 2x is equal to 3. Good. So you saw, so this is a very nice quadratic. You can factor as x minus 3 times x plus 1. Use the zero product property, x is equal to 3, x is equal to -1. All right, now you're not done yet. You need to go and see if any of these x values will create a negative inside of the input. Well, you can see immediately, if I substitute x equals -1, this will create a log of -1 here. So you will reject x equals -1, but x equals 3 is all good. This will create no negatives. All right, so the answer is x equals 3. Okay, that is all I have prepared. Now, just notice now I didn't do any of the trig stuff in this review. So just let me just put as number 9 the trig stuff, so the trigonometry from homework 9. Okay. So I didn't prepare any of that content for the review, but just be aware that trigonometry from homework 9 is on the exam Thursday. Okay. So I'm going to really try and grade your homework 9s as fast as possible so I can give you feedback on that because it is on the test Thursday. Okay, so that's all I have prepared. If anyone has more questions, please tell me. You can stick around, but just look out for the exam on Thursday and I'll send an email when it's available. Okay, it's gonna be available at like 1 p.m. on Thursday. Okay, so if you guys have any questions, please let me know.
Can you kind of go over the asymptotes, like especially the horizontal asymptote? That still got me kind of like not sure.
I'm sorry, what the horizontal?
Asymptote. I'm not sure if I'm pronouncing it right. Like the asymptote. Yes. I'm sorry, my pronunciation is not great.
Oh yeah, no problem. So for which function? Oh, are you talking about like the asymptotes of a rational function?
Yes.
Okay, so yeah, so that's not going to be on the exam. So
No. Okay. Thank you. Okay. I thought it would. Sorry.
yeah, no, it's not. If it was, I definitely would have included it in this review. So no, horizontal, vertical, slant asymptotes, no, they're not on the exam.
Thank you. Sorry for yeah.
No, it's a great question. Yeah, of course, no problem.
Could you just give us a concrete example of number 5? I just forget in what reference we would use that formula.
Yes, absolutely. So this is going to be in the context of graphing. So it's like, yeah, so it's like one of those questions where I'm like, for the following logarithmic functions, do the following. And I list a bunch of like bullet points, like those like crazy questions. So that's going to be like find the domain, find the vertical asymptote, specify 2 points that it goes through. So do you remember, I think it was question 15 of the last homework. Anyways, it's going to be a part of a larger question. But for example, it could be like f of x is equal to 2 log base 2 of x plus 1 minus 1. So I'm going to give you this function, and I'm going to want you to tell me the domain, vertical asymptote, 2 points it passes through, and a sketch of the graph. I think that's it. I don't think there's anything else. But anyways, this is going to be the context. So the 2 points it passes through, that's where you use these formulas. That's where you use these formulas. So so here, A is 2, B is 2, C is 1, and D is -1. Okay, so I got those just by looking at the transformations of the function. Yeah, so let me just do this. So the domain, first of all, domain, remember, you just set the input to be greater than 0, so x plus 1 is greater than 0. This is x is greater than -1, and then in interval notation, this is -1 to infinity. That's the domain. Vertical asymptote, you just set the input to be equal to 0. So this will be x equals -1. Good. Now the 2 points it passes through. So what was it again? So it's 1 minus c comma d. Okay. So 1 minus c, it's 1 minus 1 comma -1. Okay, so I just did 1 minus c comma d. This is 0, negative 1. And the second point is b minus c comma a plus d. And that's now, so you go up to your values. B minus c is 2 minus 1. This is 2 minus 1, comma, a plus d, 2 plus negative 1, which is the same as 2 minus 1. So this is 1, 1. So those are our 2 points. Good, and now we really have everything we need to graph this guy. So I have a vertical asymptote at x equals negative 1. I have the point 1, 1, and I have the point 0, negative 1. And that's really it. Now you just use this vertical asymptote and you kind of just make a shape like this. So that's all I would be asking for on the exam. All right, so I hope that's cool. So any questions about this example or any other questions at all about the exam?
So a circle can have any radius, but it just so happens that this one in particular just deals with a radius of 1.
Yes, exactly. Of course, yeah. There are equations for circles with any center with any radius, but the one we deal with in trigonometry is the one that's centered at 0, 0 with a radius of 1, aka the unit circle. That's the one that we like in trigonometry. Yeah.
Real quick, Professor Roberts, on this example that we did just now, how do we get b equals 1? Or, I'm sorry, b equals 2.
B, I'm going to tell you on the exam, B is the base of the logarithm.
Cool.
Yeah, I'm going to say like, oh, state the vertical stretch, the base, the vertical shift, horizontal shift. Yeah. Everything's going to be very clear on the actual exam. This is very sloppy, I know, but on the exam, crystal clear. Everything, yeah. Very cool, very cool. All right, so anything else, please just shout out to me. Of course, everyone is free to leave now. You know, this is just kind of like, if anyone has any questions, just shout them out and we can talk about them.
I have a question from the homework last night.
Okay.
Last night. I was doing it last night, so not everyone else did it last night, so I don't know why I call it that. But for problem 7, I don't know if maybe I just didn't have it in my notes, but I couldn't find the formula for it.
Okay.
Which is just to find the unknown size of the right triangle. I'm sure it's a simple formula, but I just couldn't.
Oh, okay, yeah. So this was, you're right. There actually was no question like this in the notes. This was kind of, I wanted you to take something a step further. So let's look at that. Okay, so we have A9060. Okay, so let's look at that. We have A9060. Good. And we have 10CA. Okay, we have 10CA. Okay, good. So this is a really nice question. You're right. There is nothing like this in the notes. So I wanted you to kind of use our trig functions evaluated at special angles. So we have this 60 degrees here. So with respect to 60 degrees, we have opposite. So 10 is opposite from 60 degrees. And we're looking for adjacent or hypotenuse. Here's adjacent, here's hypotenuse. So do you recall that tangent will equal opposite over adjacent? So we're going to do this at 60 degrees, and that's going to give you a side of a triangle. So let's do this. So we know that tangent of 60 degrees will be equal to opposite, which is 10, over A, adjacent. Okay. Now this is really nice because we have a definitive value for tan of 60. you want to use the trig table. So does someone know off the top of their head what tan of 60 is? Actually, it's like radical 3 or something.
Yeah.
Okay, thank you. Yeah, awesome. Yeah, so this is known now. This is radical 3 is equal to 10 over a. And this is really nice because we can solve for a. Yeah, now just solve for a, which I trust that you can do that. And now, how can we find c? So we have a, this we just figured it out. Now you can just use the Pythagorean theorem to find c. That'll be how you do that. Yeah, so this is a trickier question. I want you to take it a little step further from class, not on the exam Thursday, but just a nice question that I think any pre-calc student should do at least once. And the one right after it is really similar, where it's like the ladder against the building. It's like the same thing.
Yeah, for that, I think I got to the sine 70 degrees equals b over 15, and then I just stopped there. So
oh yeah, so you're done pretty much. Sine of 70 is b over 15.
Mm-hmm.
Yeah, so now you want to solve for b. And b will be 15 times sine of 70. That's it, you're done. That's why I said to leave it in terms of the trig function, because sine of 70 is not one of our nice values. It's not on the trig table. So just leave it as sine of 70. Very cool. So anything else?
For this question, can you actually work out the radical 3 equals 10a? I feel like I did it wrong.
Yeah, absolutely. So let me just double check that tan of 60 is radical 3. Let me just. Okay. Yes, it is. Okay, I just wanted just for my own peace of mind. Good. So we have that radical 3 is equal to 10 over a. Good. So what you could, there's a few things to do here. You can cross multiply. I don't like to cross multiply. That's not like a good thing to think of because you're just kind of blindly following steps. I like to think of this as a rational equation in the variable a, and you multiply both sides by a, which is the LCD. So you get that a root 3 is equal to 10. Multiply both sides by a. And now you'll get that a is equal to 10 over root 3. So I hope that's okay. That's what a is. And to find c, you just need to use the Pythagorean theorem. So we know that c squared is equal to a squared plus b squared. C is the hypotenuse, and I think that's what we're looking for. Yes, so we literally just need to solve this. So c squared is equal to a squared, so that's going to be 100 over 3, plus b squared. B was given to us, yeah, plus 100. Plus 100. Okay, so now I need to do this on the spot. That's going to be, okay, so far, is this good, Camille, what I set up?
Yes.
Okay. Yeah, so now you're going to want to create a common denominator of 3. So I think just write 100 as 300 over 3 and you're good. Yeah. So c squared will be 400 over 3. Okay, excellent. And now c will be 20 over root 3.